time. It's being done in Switzerland. It's 100 meters under the ground. It's about 23 kilometers in radius, or 26 kilometers in radius. It's a giant superconducting ring. It's like, I think it's got €1.5 billion budget a year. It's a $10.5 billion project. It blew up last year. We've been fixing it. And it's putting together, it's basically trying to accelerate protons and antiprotons. Oh, here's a funny one for you. So remember I said at the beginning, imaginary numbers, you remember that? Square root of x is plus or minus x? Okay. When Einstein did his derivation, when you look at that derivation, there's a point where he takes the square root of a variable and he throws away the negative result because it's nonsensical. Right? There's no reality. I can't get negative energy. There's a guy by the name of Dirac 30 years later goes, wait a second, let's go back and revisit that. Because I remember in high school that when you take a square root of a variable, you get plus or minus that variable. And guess what they predicted? That math predicted antimatter. Sure enough, a few years later, they find antimatter from cosmic rays. I mean, now we produce it, by the millions of particles, which is nothing, by the way, but we do produce it quite between these particle accelerators. So here's math predicting something that we couldn't possibly imagine, and it's real. And now we use it all the time. We're always producing this stuff. So getting back to LHC. LHC is about to produce an energy level of 14.5 tera electron volts. Now, it's not a lot of energy. I mean, not in absolute terms, but in relative terms, it's enormous. And the way we do it is by accelerating protons and antiprotons in opposite directions, accelerating them at the speed of light, and then crashing them together inside of a big, giant microscope. Okay? It's amazing. Here's something for you. So the smaller thing you want to see, the bigger the microscope's required. Right? That's pretty amazing. So why is it that we're trying to get up to 14.5 trillion electron volts? Right? Because we're trying to discover if there is something in that hard vacuum, something that makes inertia happen. It's called the Higgs field. So quantum mechanics predicts, the standard model predicts the Higgs field. It's something you can't see. It's even smaller than the atom, which is basically nothing. It's something that there's no way for us to measure it. All we can do is try and produce it. And we know for a fact that at 14 tera electron volts, we will either see it or not see it. 15 billion euros. Okay? To see or not see the Higgs field. Why is that important? Okay, so apart from the fact that the Higgs is the only explanation we have today from the standard model that can explain things like inertia, momentum, mass, right? Remember I talked about we don't need roads 100 years from now? Okay, so keep that in the back of your mind. Here's the point. All this work for the last 100 years has come to this. We've built this standard model. We've tested it the best we can. It predicts something kind of weird called the Higgs field and the Higgs particle. We know that at that energy level, we will either see it or not see it. But we know that if it exists, we will produce it. Why is that important? It's like one of those beautiful binary results. So powerful. Why? Because if we see it, we can throw away all those other crazy theories that are trying to talk around the standard model. And we know the standard model, at least to that energy level, is correct. What happens if we don't see it? It's just as exciting. I would argue it's more exciting because that means there's something wrong with the standard model. This is what it's all about. When we discover that, we will get to a very new understanding. This new understanding will probably have an absolute fundamental impact on our industry, on our knowledge, and social outcome, wealth creation like we've never seen before. We're basically dealing with the origin of mass. I mean, what I always found is that science fiction predicted a fantastic future, and when we got there, it kind of looked at it and said, actually, they weren't even close. It's far more interesting than they ever thought, right? Look at Star Trek. Look at that computer. It's a big room. It's making these funny noises and lights are flashing, right? I don't see any spreadsheets. I don't see any word processing. I just see a little piece of paper that comes out of this slot, right? That was their prediction of a computer. We kind of blew past that 30 years ago, right? So could you imagine what would happen if we actually had that understanding, the understanding of understanding what mass is and what inertia is and what gravity is, how to influence it. Imagine if we could figure out how we could equate these things together through a formula, right? Imagine if we could take all these different things and put them together. Imagine what that would predict. Well, one of the things that we've done as a team, a little over 10 years ago, I got together with some friends and an entrepreneurial physicist by the name of Howard Burton. And we got together with some entrepreneurial physicists from major universities that were disenfranchised with what was happening in their country and in their school. And we bet on them. Okay? We bet on them. We trusted the math. There was no doubt. We trusted the math. We knew that this day was coming. Because already at the time, there was a researcher on our Scientific Advisory Council who was also a Nobel Prize winner. And she was working at CERN, and she was telling me about this. I went there and saw the lepton, which was the electron, anti-electron collider that was there for the last 10 years. And she was telling me about the LHC and what it was, the whole point of that, and what that would mean to science and reality as we knew it. And that got me pretty excited. And I realized that if I bet on these people, we're gonna be doing something pretty amazing. Now, here's the best part. Canada, we're talking what? I was really excited. We're up to 36 million population. Did you know that? It's kind of small. There are cities in China bigger. Right? But we have this great landmass. We've got water, we've got oceans, we've got fish, we've got oil, we've got potash, we've got nickel, right? We got most of the fresh water supply of the world, getting back to that water thing we take for granted. Okay, so we also have one of the finest education systems in the world. We really do. What's exciting for me was I realized at the time that the rest of the world was taking physics for granted, theoretical physics for granted. They were sort of giving them these little offices in the middle of nowhere, and I went around to these universities and I found that they had offices for one physicist over here, and then another one in another building in some dark dungeon over there, and then they had 3 of them over in that building that they just sort of had space, they just threw them over there. These are the guys that are trying to figure out, the origins of mass and inertia and dark energy and dark matter, right? They're trying to reconcile all these issues. And we're sort of giving them, well, I think we have an office for you way over there somewhere. It's okay. Physicists don't need much. They need a blackboard, a desk, a subscription to a periodical, and maybe a little bit of travel money, right? They stay to themselves. And they like wine and they like coffee, and they like to get together every once in a while and discuss stuff on a blackboard. What's amazing is, wow, can you imagine if you could put all those people in the same room? Imagine if you gave them a real budget. Imagine if you get them, blackboards on all 3 walls. Because you don't want to cover the window up. They need a window, right? Can you imagine if you did that? Imagine if you paid them real salaries and you gave them real budgets for holding seminars and colloquiums and lectures, and had a staff that did that for them rather than they have to do it themselves. So can you imagine if you did that? Well, we did. We just celebrated our 10th year anniversary a few years ago. We've become probably the largest theory institute in the world for physics. We're looking at about 250 researchers and postdocs and even students. It's the largest in the world right now. It's in Canada. It's in Waterloo. any palm trees in Waterloo. We don't even have mountains in Waterloo. Like, we don't have any oceans. It's cold, right? What do we have? We have a commitment by the people of Waterloo, the universities, the Ontario government, the regional governments, the federal government, and some philanthropists who have donated between Perimeter Institute for Theoretical Physics, which is independent, and IQC, which is part of the University of Waterloo, over $600 million to the pursuit of physics, quantum mechanics, string theory, right? Because we know that over the next 5 to 10 years are going to be some major breakthroughs. And what's great about it is Canada's right in there now. We're right in there because we could afford it. See, $500 million isn't a lot of money, really. Okay? We spent that much on security for a 3-day event in Toronto. Okay? Double that, actually. But when you apply it, when you understand the value of theoretical physics, when you understand the historical value of those discoveries and what they meant to value creation in industry in our societies, when you understand the particular point we are in history right now with the LHC experiment coming, and you understand these gaping holes in our knowledge and all these contradictions, and you understand that there are people willing to spend their entire lives trying to solve these things, basically all they are ideas, and you realize that we can actually make an impact and make a difference in Canada by spending less than half of the security budget for the last G20 and G8 in Toronto. That's pretty exciting. It really is. And so that's what we've done. That's why we do it. I don't do this by myself. I have a large staff that work on this thing. It is a labor of love, but it's one where I know that there are tangible benefits for this because I've seen them historically. I've read the books. I've studied. I've talked to these people. I've seen what it's done for us at Research in Motion with the BlackBerry. Remember, 30 years ago I was in university. What was I learning? I was learning this thing called email, which I needed to know to do my assignments. And it was a cheap way to communicate with my friends that didn't go to Waterloo because I couldn't afford a long-distance phone call. So I used ARPANET, and I typed in the addresses, and I could send email all over the world. Back then it was hours. We were learning things called digital signal processing. We were learning things called wireless communications. We were learning things called CPUs, central processing units, microprocessors, memory. We were learning things like CMOS technology. We were learning things like real-time operating systems, compilers. What else? What else were we learning at the time? Well, you could kind of see where this was all leading. If you could combine wireless and digital signal processing and email, microprocessors, handheld technology, where would all this lead? Well, it led to the BlackBerry. We actually envisioned this back then. We can do the same thing now. You can envision where this stuff's going and predict it, and we can invest in it. And that's what we're trying to do at Perimeter and IQC. It's pretty exciting to see the intellectual capital we've been able to amass in terms of researchers and postdocs from around the world who've come to a city which is kind of known for a technology that's based after a berry. But here's something for you. Again, this is kind of, it's the largest math faculty in the world at the University of Waterloo. Did you know that? Nobody talks about it. It's a great place because